Once again, like I said, we are all welcome. So today we're going to look into moving forward with ML-based research projects or research or project, a quick glimpse into ML experiment in WEKA. We're going to once again demonstrate so that we want at least the majority of the class or even everybody in the class, but at least majority should be able to pick up a data set and be able to run an experiment in WEKA. So it's something that everybody can do. Like one of the targets of our presentation is machine learning for all. We want everybody to be able to take advantage of this unique technology and be able to benefit yourself in your various areas of endeavor. Either you're an engineer, you're a business tycoon, everybody can use AI or machine learning as the case may be. So this is the essence. So, and that's why again, so we are going to look into it practically today. So we're going to demonstrate with one data set, just like the present work we are discussing also is all about medical data set. It can be any data set. So what you need to get, so moving forward, we have discussed how to identify gaps. I've shown us different partitioning stuff you can use in WEKA, but then today bringing it from raw data, because I get to know that a lot of our members are struggling to be able to run simple program. We should be able to run simple experiment. So this is one of the bases for today's discussion. We take ourselves through quickly again through the basics. So where we are going to have, the first thing is to get your data ready. See, when you have your data ready, while you remember this particular procedure, this is unique and this is general in machine learning. So you start with the data preparation, which is very important. You get your data ready. So WEKA has its own ARTF file, but usually because many people are used to Excel format, so put your data in Excel as we are going to show to us. So the feature engineering is another issue there. Try to see if the features are not okay. Can you reduce it? Can you increase it? We come back to that. Then you have the data modeling, where you're going to select the algorithm. So, and then the model is done. Then you check the performance of the model. If it is not working well, it's not satisfying what you want, then you go back. You might just need to go back to the algorithm, either to do what we call optimization. See, try to check your parameter. Maybe the parameter selected is not okay. Try to do hyperparameter tuning, and then go back again. And sometimes, no matter the hyperparameter tuning, sometimes you might need to change the algorithm. ANN is not working for you. Why don't you try SVM? So this is why you have this tekrar. This is a kind of looping here. But sometimes your looping might have to go back to look at the feature engineering. Maybe you are using wrong features, which might make you not be able to get what is, we will make you not to be able to get what you are expected to get. So you have to go back to feature engineering. Then sometimes you might have to even go back to data preparation. Maybe the data that has been given to you is not good. It has a lot of noise, or it could even be a wrong data you are modeling with. Because I've seen a situation whereby someone was predicting a wrong parameter. Now, that is why now I'm going to open for us the small data set. We can see, I believe everybody can see the data set now in Excel. So you can still look at this Excel file. This is an example. You can prepare your data in this format. So you can see here, we have the first column there, that is the age, which is an attribute. Then you have the gender, you have other DC, polyuria, polydipsia, and also for other medical terminologies, because this data set is about trying to predict if somebody is having diabetes or not by using just questionnaire. These are questions you can ask people easily. Now, so you can see these are all the inputs, or what we call the independent variables. That is independent variables. So why this is the independent variable? This is the class. Is that a positive? Positive, and then you are going to have some negative also. Yeah, we have some negative. It means they are not having the disease. Now, So when I mentioned to the fact that sometimes you might need to go back to the program, to your data set entirely. If you put this data here, let's say obesity is here. See, you move obesity to the last column. Then if you load your data, because WEKA will automatically select the last column as your class. So you'll be predicting obesity instead of predicting the actual target you want to predict. So we need to avoid this kind of mistake. So that's why sometimes you see someone that is, they put the class of some people put class here. See? So if you load your data, now we're going to open WEKA now. Let's open our Explorer. Let's open our Explorer. So this is our Explorer. And maybe somebody will ask, how did we get here? This is the, once you launch WEKA, this is what you get. Immediately. Now, so once you launch WEKA, this is what you get. So you click the Explorer. So the Explorer gives you this. And then the first thing there is to try to open the file. So you go to the location of your file. So if you start the opening initially, this is what you get. So you select the location where you want to open the file. Yeah. Because I already select here. Sometimes when you point to your file, you might not see your file. You need to make sure you are saying show all file or show me CSV. Otherwise, the default value is this. So even when you go to the location of your Excel file, you will not find anything because by default, WEKA is looking for .arff. So you need to make sure that this is pointed to all file. Then you can open your data file as the case may be. Now, having opened that, now you can see these are the attributes. The same thing we earlier checked in the Excel file there. You can see the age. So by default, the last column is taken to be the class, the one to be predicted, which is positive or negative. So if you arrange your data in such a way that you don't make, I always ask people to make sure that the last column is what you want to predict to avoid mistakes. Sometimes you just load the data and you forget. So if obesity is the last one, then you'll be predicting obesity, not knowing actually you are predicting the wrong thing. In that case, there's no amount of optimization you do. In fact, sometimes you might even get good results, but what you are reporting is not what you are supposed to report. So we need to pay attention to that. Now, once your data is loaded, so of course, that is having checked that your data is okay, everything is fine. So then you go in to the classifier. You can see here, once this is the processing stage, getting the data in, then go to the classifier, classification area. It could also be regression area. It's okay. The next thing is you must have decided based on your literature review. Maybe someone used this data before and they divided the data using 70% training, 30% training. It's always good to follow the earlier work. Even if you want to use n-fold cross validation, it's okay. It means you want to do two experiments, one with cross validation, another one with the holdout method, 70% training, 30% testing, or three, training, testing, and validation, depending on what the earlier researcher used, because it's always very important. You want to compare your work with the earlier work. So that's why you need to use the method they also follow, in addition to whatever you want to bring to it, because sometimes you want to try to justify that. No, although they have used cross-validation, but I think the data is really big, we can do with just holdouts. You can put your two results there, one using cross-validation, the other one using holdout, and then you compare your work with its own, the one that are similar. And then you can now extrapolate and try to see why your new method is better than what they used earlier. Now, so the next thing is, now you need to select the classifier you're going to use. If you remember here, which was earlier here, See, once you have it, the next is to select the algorithm. This is here. So we have inputted, we have prepared the data now. We brought our data in. Our feature is okay. We don't need to engineer anything again there for now. So the next is to select the algorithm. So which in WEKA, as we have opened, you go here, here you select here, click here. See, choose. Default is 0. It's another classifier. But let's go in here, and then we have also several of them here. This is based systems. We have the functions. So like the support vector machine are there, regression. We usually have the meta. The meta one is the ensemble. We have different, there are a lot of them. So as usual, we always recommend to start with simple classifier. So I go to what we call lazy. That is a group of classifier called lazy. So one of it is the IBK, the K nearest neighbor. Show me your friend, I'll tell you the kind of person you are. You can see here. So you can just put your mouse over it to show what is inside it. So this is K nearest neighbor classifier. So I want to use that. It's very simple. So now the next, once we have selected the algorithm, the next thing is for you to select the type of data partitioning, which we discussed a couple of maybe 2-3 weeks ago. So how to select it and what it means. This is the percentage split. Let's say we want to use 70%. Then the remaining one is going to be 30%. So, or you want to use cross validation, which could be 10-fold or 5-fold, as the case may be. Okay, let's start with percentage split. Let's say the person who did the experiment before, he actually used 80%. Yeah, if I remember vividly. Yeah. So 80% for training, and then the remaining 20% is going to be for testing. Now, that's all. So we go. The next thing is you are ready to start your experiment. So it's very, very simple. So like I said, I want everybody to be able to practicalize this. See, just made very simple setting now. Just click start. Then you run your first experiment. See, and these are the results. You can see the result here. See. See, but may I mind you, this is the result of the testing set. This is the result of testing set. It doesn't show you the result of training set. If you want to see the result of training set, because then you need to go to more option, and then you can see here, you select this option. Output models for training split. You want to see result of training split, then you have to check this option. But usually, because what is more important is the testing set, because even when you get very good result in training set and you are not getting good result in testing, that is overfitting. We don't want that. Once your result is good in testing set, then that means you are in a good shape, hopefully. Now, you see the first experiment is already delivered. So and then you can check the results. It gives you the time taken to build the model, to evaluate the model. So this is the time taken. Now you can see correctly. You can see something there. It's a time taken to build the model is 0. Time taken to evaluate is 0.03. Because lazy classifier like k-nearest neighbor, there's no building of model. It's only take your data set and store it somewhere. So during evaluation, it will be comparing the testing set with the k-nearest neighbor principle and then getting the result solved. So I recommend that we can try to check out our earlier video on k-nearest neighbor, how it works for those people that might miss that. So you see how k-nearest neighbor works, very simple, and sometimes could be very powerful, especially for data set that is just coming for you to you. It's good to start with k-nearest neighbor. It's a very simple algorithm. So now, so we can see here now, number of correctly classified instances is 99. The mistaken instances is 5. You can see 95% accuracy. So you can see all other performance measures are there, as the case may be. And most importantly, here, you can see the confusion matrix. Confusion matrix, these are the 3 mistakes. This is positive, this is negative. You see? So this is positive and this is negative, which means this is going to be a false negative, and this is false positive. That is, this guy is supposed to be positive, but is predicted to be negative, which is a serious mistake in medicine. So there are only 5. Maybe we want to do more. Once we have run the experiment, then the next thing is, okay, maybe you need to do hyperparameter tuning. You see, as we showed us earlier, see, sometimes you have to, you check the performance. 95% is good. This is excellent, by the way, but doesn't mean you have to stop there because you are yet to tune the hyperparameter. So you go back again, go back here, you take this path, see here, to the modeling back, which here we just go back to, yeah. Yeah. So in WEKA here, we need to check the hyperparameter values. K-nearest neighbor present us with 2 major hyperparameter values. Here you can see, just click here. How do you see the hyperparameter values? Just click here. Then it shows, you can see KNN. This is number of neighbor that you want to use. It's using presently 1 neighbor. That is comparing every instance with another, with each of the neighbors. And whichever one is closer to you is let the class of that neighbor that is closest to you will be your class. So it means if a neighbor has been stored to have from the training data set, we have a neighbor that is closest to one instance, and that neighbor is diabetes. Then it's going to classify the new samples as being diabetes. So that's why sometimes it's good to increase the number of neighbors. So since it is a 2-class problem, class A, class B, positive or negative, so usually it's good to have odd numbers. So you need to change this value. K, we have batch size, core validates, all these are parameters. See, to differentiate between hyperparameter and parameter. These are just parameters. You put any value here, it sends it to the back end of the code so that the program can run. However, these hyperparameters, they are the parameters that will affect the performance of the algorithm itself. For example, somebody is saying, show the result in 2 decimal places. Either you make it 2 decimal places, 4 decimal places, it doesn't have effect on the performance of the algorithm, by the way. You are just trying to round up the numbers, which is okay. So this is not an hyperparameter. So, but this is hyperparameter, the number of K. And the other hyperparameter that is very important there is for you to select the distance function. Which kind of distance function are you going to use for your algorithm? So we have different options here. We have Euclidean distance, shape distance, Manhattan, Minkowski, and host of other distance measures that could be available. So these are the 2. The distance measure is good for you to optimize it. But here we start with KN. How many neighbors do you have? Okay. The experiment we have earlier was done using the default, which is 1. Now I change it to 3. Okay, and you run the experiment. See, the experiment is done. See, strangely, you can see that the performance goes down, 93. Okay, so we go back again. We check for 5. Okay, then you run. You can see there, it seems it kept going down. So that is why I always say, this is hyperparameter optimization. You are trying to optimize the value of K nearest neighbor that you are going to use. It seems for this problem, K is equal to 1 is working fine. You might have your own data set. 1 might be the worst. As you increase the number, the performance keep increasing. Then it gets to a place, it goes down. Then you stop just before it starts deteriorating in performance. This is called simple hyperparameter optimization procedure. That is, you make it very, very simple. So you search it manually. So you do for 7 again, maybe you're going to get improvement depending on the data set. You see, sometimes it fluctuates a little bit. Okay, I go to 9. You can see jump down to 89. It means the more as you are increasing the parameter, the hyperparameter value, it doesn't make good contribution to the model you are building. So then after you have to check a couple of values, 1, 3, 7. So you have a small plot. Usually I recommend to people have a small plot that will show you that the performance was going up and then it goes down. For this case now, we got the best when K was set to 1. So we are done with that. So since we realized that 1 gave us the best, we keep 1 as our default value. So we run the experiment once again with 1, and you can see here, we still have the 95%. Then it's time for you to go inside and change the distance measure. Euclidean distance is what the default value. Go choose shape distance measure, and then see what we get. Say you run the code once again. You can see here, shape also brought down the performance. You note it down. It's good to have a small plot so that as you are going, you'll be able to monitor which of them is going to be our final option to be selected. So I go to Manhattan. Okay, Minkowski, as the case may be. Then we run it again. You can see there now, it goes up again. You see machine up. We still have more left to choose from. So this is called the simple hyperparameter optimization. You see, you try to check, am I getting better result or am I not getting better result? So this is how you can run a very simple experiment in the WEKA environment. So get your data ready. Select the partition method you want to use. If it is cross-validation, as the case may be, we have discussed this, select it. And if it is this one, depending on what is in literature or the work you want to compare your work with, select it and then go into your experiment. And then sometimes also, maybe like I said, we choose the k-nearest neighbor to be an example because it's very, very simple. It's very, very simple. We have discussed this severally. So for those who might miss it, we can refer to videos on the k-nearest neighbor algorithm and how you can run it. So by this is that anyone should be able to pick up a data set, prepare it in a CSV file, then which is a special type of the classical Excel, save it as CSV, and then load it into WEKA, and then you start your experiment. So, because I've seen lots of groups, you have in the groups, in the research group we had, some of you have been able to identify the specific data set, but having problem moving forward. Let every member of the group try to run something and then report back to your group what you have done. Okay, this is what I'm getting. So you can distribute it. Someone can use k-nearest neighbor. Another one might decide to use, okay, let me use not k-nearest neighbor. I want to use tree. You go to tree, we have decision tree, the very popular one, the J48. Okay, select it, and then you start running your work. See? So this one is getting 92%. Depending on the algorithm you want to use, you have to keep checking. The good place to actually try to start is try to implement what the earlier researcher did on the same data set. Try to see what, are you able to reproduce what they have done? It's very, very important. A good research work, you should be, if it is a good research work, you should be able to reproduce what they have claimed to get. See? Because sometimes some people make claims that might not be real. So you'll be struggling to achieve what better than what they have achieved. Meanwhile, how can you achieve better than someone who didn't do anything but just cook up results? This didn't happen, unfortunately, in research world. So that's why you first of all try to reproduce what has been done. You are able to get it based on the algorithm you use. Oh, that is good. Then you now think of how can I improve upon it? Can I improve it using simple algorithm? Or do I need to do a kind of mixture of different algorithm. This is where you have to keep checking in here back and forth. So like I said, when the performance measure is not satisfactory, try to move back to the modeling, change the hyperparameter. We have discussed that. We have discussed the hyperparameter, change the hyperparameter. If maybe that will give you better result. If it's not working for you, maybe it's time for you to change the algorithm. Run different algorithms and try to see the one that will work for your data set. Because I always say, let the data speak. No one can just tell you which algorithm will work for me. There's no algorithm that works for every problem. It's not possible. If anybody tells you the best algorithm you should always use is this, no, that is against the principle of machine learning. So you have to let the data speak. Put in your data to the platform you are using, and then try to run the experiment and see what you can get. If it's not working for you, go back and do hyperparameter optimization. Very, very important. If you don't do hyperparameter optimization, you are not being fair to the algorithm. You are just declaring that this algorithm is not working. Meanwhile, you are the one that has not been able to select the appropriate value for the hyperparameters. So this is very, very important, but it's compulsory, by the way. Otherwise, the reported result will not be valid because you are not being fair to the algorithm. I've seen someone that will optimize. He used like 3 algorithms. He optimized A, optimized B, but did not optimize C, and was comparing the results. I said, no, this is unacceptable. The result is not valid. You cannot compare the result of optimized algorithm with another one that you refuse to optimize. Because it's like you didn't give someone the opportunity to display his best, and you are condemning it that it's not working. So we don't do that as far as machine learning is concerned. So once your data is in, you do your modeling, then there's opportunity for you to do a lot of repetition, looping, coming back, checking the hyperparameter, changing the algorithm. And if the worst comes to the worst, you might need to go back to change the number of features as the case may be. So this is a very simple, what I call a quick glimpse into machine learning experiment in WEKA, and I use it to be able to encourage every one of us to be able to do something. Let's get our hand on something, get a data set. I posted the same data set on the WhatsApp group. Pick a data, try to reproduce the result, try to do something on that. And then if you have any other question, query, or something that is not is clear to you, you are free to bring it up, or also to contact us whenever you are. Like the essence is that we want everybody to be able to benefit or take benefit of machine learning in your various or individual area of specialization. I know some of our team members are already doing very great work, but I don't want anybody to be left behind. This is the essence of this quick revision on making machine learning experiment in WEKA a very quick guide. So I'll give room for question at this point in time, if anything is not clear. So thank you very much for being there always, and I wish you all the best. Thank you.